In this video, you're going to learn about how memory works inside containers. The two options that we're going to use for Docker are -- memory and memory swap. The memory is the total amount of memory that your container can use. So if you have multiple processes running in that container, then it would be the sum of all of those processes. Once you use that amount of memory, if enabled, your container can swap. Most of the time in production environments, swap will be disabled at the operating system level, so you don't need to worry about it. But if not, you have to set memory swap equal to memory, which essentially disables swap. No one wants a JVM swapping out its heap. It'll make it behave very badly. We learned in the JVM ergonomics section that most JVM memory settings happen automatically based on the resources of the host. If you're using an old version of Java, so prior to Java 8 update 131, all of those ergonomics will be based off the host memory, not the amount of memory that you give to your container. So if you give your container 2 gigabytes, but it's running on a host with 128 gigabytes of RAM, then it will pick its heap size based off the 128 gigabytes of RAM, which will pretty much always result in it being killed, so out of memory killed by the container runtime. Assuming that you're on a later version of Java, so the latest version of Java 8 or any version beyond that, then the JVM picks up the container memory well, and it bases its ergonomics off that. So you don't need to change any settings. However, there were additional flags added in Java 10 Plus for being able to tweak the ergonomics, which you might have to do. The reason that you might have to do that is the memory that your JVM uses is not just the heap. It's also threads and metaspace and code, and the garbage collector uses memory, as well as your application might allocate native memory, both via byte buffers or via Sun Misc unsafe. Threads is an interesting one because by default, the thread stack will be allocated to a megabyte. So if you create lots and lots of threads in your application, you can end up using a lot of memory that isn't heap. So suddenly you might need to tweak some of the ergonomic settings. We're going to demonstrate this in one of the demos by having Docker kill our container for using too much memory, even when we don't allocate a single thing on the heap. One tool which we're going to find very useful for diagnosing these types of problems is native memory tracking. That is a tool built into the JVM that you can enable, which can give you an output of how much heap, how much class space, how much memory threads are using. So even if you don't quite understand what some of the code in your application is doing because it's hidden in a library, you can get an idea of how much memory it's using in each particular type. To demo the memory part of running Java inside a container, we're going to use a slightly more complicated application. It's going to be able to either allocate off-heap memory, or allocate a lot of threads. And we're going to pass in as a parameter to the application which one to do so we can keep running the same application. One of the first things this application does is print what it sees as its total memory, max memory, and free memory. It also does a sneaky trick to get hold of the RAM on the box. Our max memory is our max heap size. So remember, from ergonomics, we want that to be based off the container, not the amount of memory that's on the machine. So for allocating off-heap memory, all we do is allocate using a byte buffer, and then we store that direct byte buffer in a list so it doesn't get garbage collected. To create threads, we just have a for loop which will create 1,000 threads each time, and it will sleep between each invocation. Let's make that a bit smaller so that we don't need to wait for that. So every 100 milliseconds it will create 1,000 threads. Each time it also logs out the heap size. And then finally, for allocating heap memory, we just allocate byte arrays, each with 100 megabytes inside, and we put them inside a list to make sure that the lists do not get garbage collected. Now let's just have a look at the Docker file that we're going to use for this. Previously, we'd flipped between using entry point and command, but we have to use an entry point this time because what we want to be able to do is rerun this Docker container with many different parameters, with threads, with off heap, and with heap. And if we use an entry point, it means that when we run our Docker container, whatever we pass as the command there will be passed as the command to our startup script. We'll start off testing with an old version of Java 8, and then we'll switch to using Java 11. So, first off, let's build the image. So we'll use our normal Docker build, and the submodule this time is the memory. So memory:docker. And then let's try and run it. So remember that we're using quite an old version of Java 8 initially. Let's run it with a memory limit of a couple hundred megabytes initially and see what happens. And we'll start off with the heap allocation. So the same as your regular Java objects that you instantiate. We're also going to give it a name, and this is so we can easily run docker inspect. So what happens? The first thing to note is the virtual machine that's running Docker has 4 gigabytes of RAM. And we can see all of that. We can see the 4 gigabytes. And more importantly, our max heap size, our max memory, has been set to just below a gigabyte because Java ergonomics default to setting a quarter of the host's machine as your max heap. But we don't want it to base it off the host machine, do we? We want it to be based off the container memory. And we can see that this version of Java, so quite an old version of Java 8, it pays no attention to the memory that is allocated to your container. It's just doing ergonomics based off the host resources. The other interesting thing to note here is that even though we gave a memory limit of 200 megabytes to our container, we were able to allocate quite a lot more. It was on the 5th allocation statement that eventually this container was killed. So what's happening here? And what's happening is because we haven't disabled swap, our container has actually been allowed to swap before it was eventually killed by exceeding the memory it was allocated in its control group. So we fix that by specifying both memory as 200 megabytes and memory swap. So that doesn't mean we get 200 megabytes of swap. It means that the total memory, including swap, is 200 megabytes. So this effectively disables our container from swapping. We'll give this one the name memory-swap, and then again allocate heap memory. And probably as we expected with the first one, it was killed after 2 allocations. So we no longer got to swap. What we want to do now is see why it was killed. Why did our container stop? So if we quickly run docker inspect, scroll to the top, there'll be a reason. And we can see here that we were killed. So it wasn't a Java out of memory exception, it was the container runtime. It was the control group that resulted in our Java application being killed. This is not what we want. First, we'd rather our application never be killed, but if we run out of memory, we'd rather use the Java way of running out of memory that we're used to debugging. We'd rather see a Java out of memory exception. So fortunately, this behavior is much better inside Java 11 and later versions of Java 8. So let's switch to Java 11 and rebuild our image and see how that behaves. So it'll just take a few seconds to build, and then let's run the same experiment. So we'll run a docker run. We need to remove the old one because we're going to name it the same. We'll do a docker run with a gigabyte this time. And we can see that rather than being killed by Docker, we get the thing we're used to. We're getting an out of memory error. And the reason for that is that we can see that our max memory, because we've specified a gigabyte for our container, is actually set to 250-ish megabytes. So ergonomics have been based off the container memory, no longer the host, which means that Java can work out that it's run out of memory before it's killed by the container. And we can validate this by running docker inspect, scroll up to the top, and this container should not have been killed. because Java itself has decided to exit because it realized it's out of memory. So Java 11 and later versions of Java 8 behave much better in respect to container memory. Now that heap is working, let's do some experiments with the other types of memory and see if we get the same good behavior. So we can first start with off-heap memory. We can specify a memory and a memory swap to 400 megabytes, and this time we'll pass in the name off-heap so we can inspect it later, and we'll also pass in off-heap as the parameter to the application, because that will mean it'll start allocating the direct byte buffers. Okay, this looks good. The max memory has been set properly, and we see we get a different type of out-of-memory error, one for direct buffer memory. So we can see that the ergonomics in Java have correctly set the reasonable size for the direct buffer memory. We can validate that the container runtime was not involved by just running a docker inspect and then have it looking for killed, and it wasn't killed. So does this mean that in Java 11 we never need to have a look at our container runtime to see if we've been killed? Not quite. We've got one more memory type to try. So we're going to run with the same memory settings, so 400 megabytes of memory and no swap. We're going to name this one threads this time. Now remember, threads do use memory. They have to allocate a stack of a megabyte. So we can see that eventually the application just stops, even though it was meant to do this forever. And if we run a docker inspect on this one and we go up, we'll eventually see that the runtime, the C group, did do an kill. And that was because the memory wasn't heap, it wasn't direct memory, instead it was memory used by threads.